In this next video, we're going to talk about arguments based on samples. Arguments based on samples share a common form called inductive generalization. Other names for this same form are simple induction, induction by enumeration, and statistical generalization. Inductive generalizations are arguments that go from the particular to the general. Inductive generalization is the argument form used in political polls forecasting election results. Before an election, poll takers interview a sample of the population of registered voters, and on the basis of what members of the sample say about how they will vote, the pollsters predict how the population will vote. So here's how the pollsters' reasoning goes in reaching their conclusion about how people are going to vote. Or here's an example of how it could go. 1,200, that is 60%, of the 2,000 voters polled plan to vote for the incumbent. That's the premise. And then the conclusion is drawn about the general population. 60% of all voters plan to vote for the incumbent. Here's another example of an inductive generalization. 98 out of 100, that is 90%, 98% of receivers that were examined were without defect. That's the premise. Conclusion: 98% of the receivers produced at the plant are without defect. Generalizations that are conclusions of arguments from samples can be either universal or statistical. Universal generalizations state that all, 100%, or none, 0%, of the members of a class have a certain property. Statistical generalizations state that some percentage less than 100, but more than 0% of the members of a class have the property. Remember that statistical generalizations can also be expressed using vaguer terms like most, almost all, or very few. So the two examples we looked at before, the one about receivers and the other one about voting for the incumbent, both share the basic form of an inductive generalization, and that's this form, where the one premise is X% of observed F's are G's, and the conclusion, X% of all F's are G's. The conclusion of an inductive generalization states that the percentage of F's that are G's in the population is the same as the percentage in the observed sample. So here the observed sample refers to the percent of the total members of a class sampled in the premise, and then the population refers to the entire class being discussed in the conclusion. For those of you who like think about things pictorially, the relationship between a population and a sample looks like this. So you've got the total population that you want to discuss, whether it's the receivers made at a factory, all the receivers, or all the people who are going to vote in an election. And then you take some subset of the individuals in the population, and they're your sample. They're the ones that you collect data about, and from the data you collect from the sample, you draw conclusions about the population as a whole. Whether or not an inductive generalization is likely to lead to a true conclusion when the premises are true depends largely on whether or not the sample mentioned in the premises is representative of the population referred to in the conclusion, whether or not it is representative of the whole being spoken about. When a sample is representative of the population from which it is taken, the conclusion based on the sample is strongly supported. To say that a sample is representative is to say that the features of the population that concern us in an argument are reflected in the sample. When this is the case, what is true of the sample will probably be true of the population as well. Traditionally, the following criteria are required for representative samples. First, the sample must be large enough. And second, the sample must contain sufficient variety. And it's pretty easy to see why these things are both needed in order to have representative samples. For example, polling 5 potential voters in what they plan to do in an upcoming nationwide election is clearly not a large enough sample to make any useful conclusion about how all the voters are going to behave. However, what counts as good enough? It is a contextual matter. So polling 5 out of 7 members of the board of directors for a small company about their plans in an upcoming board meeting vote that would probably be a sufficient sample to draw a conclusion about what board members are going to do. But a large sample size isn't enough on its own. For example, if one polled 100,000 people about an upcoming national election, if all those polled were wealthy business executives, the sample would still not be representative. It'd be skewed in the direction of predicting what wealthy business executives will do, which is going to differ from certain other segments of the population. But then Gallup and Harris polls usually polls less than 2,000 people and are able to generate very accurate predictions about national elections. Why is that so? It's due to the variety of the samples. Gallup and Harris take a smaller number of people, but make sure that they're representing a wide variety of people, and they get much more accurate results than one would get even if you had a much larger sample, but had a lot of uniformity amongst those being sampled. Certain methods of sampling are more likely to lead to representative samples than others. One method of sampling that, when the sample is large enough, will likely lead to a representative sample is random sampling. In random sampling, each member of the population has an equal chance of being chosen as a member of the sample. So, take for example a random sample of students at a university. This can be generated by printing each student identification number on a different ticket, mixing the tickets in a rotating drum, and performing a blind drawing of tickets to select a sample of the desired size. It's the type of thing when Yolanda Vega, the New York Lottery, picks out lotto numbers. They're all in this thing, and there's an equal chance that any number will be selected. A special type of random sampling is called stratified random sampling. This form of random sampling is useful when information is available about the nature and variation of a population. So when we know something about how segments of the population will be apt to differ with respect to the property that interests us in the conclusion, and when we also know the proportion of each segment in the population, we can stratify the different layers in the population and select randomly in each layer. So, for example, if you're asking a question where you know that men are likely to give a different answer than women, it would make sense to figure out what percentage of the population you're talking about is male, what percentage is female, and then do proportional segments of both the male and female portions of the population. When an argument is based on a sample that is too small, it is fallacious. This is called, sensibly enough, the fallacy of insufficient statistics. It is also known as a hasty generalization or leaping to a conclusion. When an argument is based on an unrepresentative sample because the sample lacks variety, that argument is also fallacious. This type of fallacy is called the fallacy of biased evidence. Because when you've got a lack of uniformity, you're overrepresenting certain segments of the population and underrepresenting others. And this is going to lead to biased evidence in the direction of the portion of the population that you've got overrepresented in the sample. Sometimes, even when the statistical evidence indicates that choice A is a better choice than choice B, if we have vivid anecdotal evidence, for example, a personal account from a friend that favors choice B, we may give too much weight to this anecdotal evidence in favor of choice B. When we allow this small amount of particularly vivid information to outweigh a substantial amount of statistical support for a conclusion, we commit the fallacy of misleading vividness. So the example your book gave was about someone who's collected a whole bunch of information on cars. They're going to make a car purchase, and they clearly see, according to the stats, that choice A best suits their needs. But then, if they hear a story from a friend about what a bad experience they had with car A, they may overweigh that evidence against choice A and go with choice B, even though that single anecdotal piece of evidence shouldn't outweigh all the evidence in favor of A. That would be an example of the fallacy of misleading vividness. And there's a good psychological explanation for why this happens. Our brains just process information like personal anecdotes from friends in a different sort of way.